hey, we're going to do disk method, x-axis revolution. We're going to play around a little bit, see what happens. So to do this, we're going to do some stuff in Desmos Classroom. So here's what I'd like you to do, is go to student.desmos.com, log in with Google, and enter that 6-digit code. What that'll do, again, for those of you, or yeah, this past fall we did this as well. We did like for one activity in this fall, but we're gonna do it again. It doesn't matter how many Desmos classrooms you're in. Every new one you're in, it basically only affects on the teacher side. It affects what activities you push out to you. That's it. So you can be in like 35,000 of them, but as long as only one is pushing stuff out, it's all good. So I'll give you some time to go do that. And then enter that code. And once you do that, there's one activity in there for you that you can get into and start working on the first 2 or 3 slides. Again, as you have questions or if you need help figuring something out, please let me know because I want to make sure you all get there. All right, looks like, oh, there's 7. Cool, we're getting there. Give you a little bit longer before I start reaching out to people that I don't see in the chat or don't see in the classroom. Sweet. We got 10, so it means I'm waiting on 3 people. Looks like I have everybody in the person there. 1. Oh, let me double check that. Disagree. 1, 2. Never mind. Everybody in person's in. Ooh. Heck yeah. All right, I'm waiting on 2 people, it looks like. Just gotta figure out who it is now. You know, it'd be helpful instead of time enter. So up a name. Again, folks, once you get in there, or it looks like we're waiting on one more person because there's one person not here today. Once you get in, start answering slide 1, 2. You can only go through 4 right now. So start working on slides 1, 2, 3. We're going to stop and pause. We're going to talk about them in a little bit, but I want to make sure people have something to say about slides 1, 2, at least 1 and 2. And you probably could go even further than that.
Okay, sweet. I think that's everybody. Because we have one absent, I'll have to make sure I send them the code. Okay, so at least it's animating. That's good. I wasn't sure if it was. One, 2, 3, 4, 5, 6, 7, 8, 9. Looking on 3 more people to respond to slide 1. And then we're going to start chatting. One, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, still 3 more. Open another one over here. Hey, people are in there. That's not what I wanted. Activity history. All right. I'm going to pause you in 5, 4, 3, 2, 1. You'll have an opportunity to change some stuff later, but first I want to share with you a couple different things. Start with number 1. So, what is the radius of this cylinder? 5. So we had a couple people that were thinking it was 3, but the majority of us are, again, thinking it's 5. Because if you see the full, like in the teacher view, it's not showing the animation. But when you're looking at it, you can see that it starts up here, it's rotating all the way around and coming back. We're making a cylinder by taking this a little region and rotating it. Cool. Oh, where'd it go? I want it right there. So here, so this question is, it's particular about where you're cutting in and how you're cutting it. If you cut a cross section of this figure perpendicular to the x-axis, so straight up and down like this, what shape would it have? And for the people that have responded, our consensus is that it's a circle. I'm going to unpause you at this point so that you can go and change that or add that in as you see fit. It is a circle. It should be a circle. And I mean, when you see that revolution, yeah, I saw who that was and I figured they probably wanted to change it. But it's a circle. Hey, there you go. So there's at least 1 or 2 other people adding stuff in. Cool. I give you 5 more seconds before I pause you again, because then we're going to go into slide 3. But it should be a circle. When you cut it this way, when you see the full revolution, go to the student version. You cut it like this, you're going to get a circle. That's the big thing we wanted to see there. Building up an idea. All right, I'm going to pause you in 5, 4, 3, 2, 1. All right. Now we're going to look at the area. What's the area of one of those cross sections? So there's a couple different answers you could have given. I don't know. The exact area is what we had about 5 people give us, 25 pi. Because the radius is 5, the area of a circle is pi r squared. So exactly it's 25 pi. These last 3 are relatively, those would be accurate to 2 decimal places. Remember, when we do stuff in calculus, you need to be accurate to 3 decimal places. So if you were one of those, you should double check that and make sure you're accurate to 3 decimal places. So I'll give you a moment to change that. 25 pi is perfectly fine. 78.53 or 54 would be fine if it was to 3 decimal places. If that was the AP test, technically your answer would be wrong. So you want to make sure you don't mess with that. Okay? Which is also the nice part about just leaving an exact answer, because then you don't have to remember, oh crap, I need 3 decimal places. Cool. So we have that. And again, this is so that we can make sure that we have, this is something to refer back to. I'm going to pause you in 5, 4, 3, 2, 1. Doot. All right, so that's the area. That's the area of one cross section. Just saying, well, the cross section is a circle. The area of that cross section would be 5 or 25 pi. What about the volume of the whole thing then? And we have a couple different answers here. I'm betting some of these are just this multiplied out. But we got 150 pi. Well, because we know the cross section, the area of the circle would be 25 pi, but the height of the cylinder is 6. So you just multiply by 6 and that's how you get it. Again, the exact answer is nice because you don't have to accidentally get it wrong by only having 2 decimal places. And I'm sure this is 150 pi, 150 pi, 150 pi. So I'll unpause you so you can fix that real quick. All right. So now that we've done that, what I'd like to do is we went through pretty simple function. Again, our function was just f of x equals 5. What if we took a different region? Because technically what we're doing in this is you see this rectangle right here. We took this rectangle and we rotated it around the x-axis to make a cylinder. Well, what if the region we're rotating isn't a rectangle? How does that look? Now, this process we just went through is going to be pretty darn similar for any other region. So what I'd like to do is have you move on to 5 through 8, where you're going to play around and see what happens when it's a region other than that. Okay? I'm going to give you I'll give you a little bit of time. I'm going to monitor you from the back and from the front and just kind of monitor and see where you're at. Okay, go. Most people are past that. I'm trying to figure out the radius. Seeing a lot of nice responses in slide 6. Awesome. Seeing some really nice things, some thoughtful responses. We're still working on 8. That's okay. You know what I'll do is I'll let you keep thinking about that one. Folks, I'm gonna give you about 2 more minutes, and then we're gonna come back together and double check what we did on 5, 6, and 7. And then we'll work through 8 together. But try 8 first. To start typing in integral, you can type in int, and it'll throw a definite integral in there for you. You can start putting some pieces of information in there. Again, if you're not sure, at least put the int in there and with the dx, and we'll talk more about that in a moment. Sweet. People are putting that stuff in there. About 20 more seconds. All right. I'm going to pause you in 5, 4, 3, 2, 1. I waited a little longer because I heard someone typing. All right. 5. So our general consensus again is that when you cut this, do a perpendicular cross section. So in this case, cut it straight up and down. You're going to get a circle wherever you're at. Now, it may look, again, the perspective is always hard whenever you try to represent something 3-dimensional in a 2-dimensional setting. It's always hard to do that. But we're doing the best we can here. And the animation kind of helps us see that. So this should be a circle on slide 5. So this one was what I was really happy about, the variety of answers and how well they are. So we're going to go through each of them. So as x increases, the radius increases. It's the distance from the curve to the x-axis. Exactly. Like as this keeps going, or if we went back to say slide 3, like the radius is still whatever the distance is from the x-axis here, because that's where we're rotating around. The radius is the x value squared. All right. The radius is the length from the x-axis to the top or bottom of the shape. That's true. The radius is x squared. The radius is x squared. All parts of the graph are x squared. Cool. They're increasing exponentially as the value of x increases. Almost exponentially. It's to the second power. It's increasing quadratically. X squared. They are all equal increments away from each other. Because if you look, these are all, I'm not even sure how far apart each of those are, but each of those x values are equal parts away. That's very fair. So there's a lot of different ways we can say this, but generally the radius of each of those is whatever the height of the function is. And in this case, it's x squared. And since we know the radius, we can figure out the area. So I'm really looking, let's see. Yeah, so like we look at pi times x squared squared, pi times, probably one less pi there, but pi times r squared, pi x to the 4th, which is simplifying it, x squared squared pi, pi r squared, pi y squared, which y in this case, y equals f of x, and f of x is x squared. Boom. So for area, and I'll let you change your things right now, some version of like pi times x squared squared or pi times x to the fourth would be a good thing to put here if you didn't have something like that. So I'll give you a hot second to fix that one or to change that one. So you can come back and look at that. And remember, that's the area of one of those cross sections. So the difficult part here is, well, with the previous one, we had a consistent, like we had a consistent width. Oh, we have a consistent width here, a height of the thing in the previous one, and we do here as well. But the problem is the radius changes, and how do we account for that? And that's what the integral is going to help us with. So let's see what our responses are. Sweet. So looking at our responses, there's a lot of good things in here. And thank you everybody for everyone who had something in there. These are all generally the right idea. I'm going to pick on Jean Taylor, and we're going to edit theirs a little bit because it's, I think, the one closest to what I'm super looking for. There's a lot of good stuff there. To fix Jean Taylor's, let's flip the 0 and 3 and then put a dx right there. So you can do that as well. It's like Herman Grassman almost had it. Just to have to put the dx at the end. Boom. Ooh, get rid of that extra 3 there. There goes Jean Taylor. Hannah Fry base almost has it. They just have to have the dx there. Gottlieb Frege just needs the dx. He O needs the dx at the end. Ismail Mustafa El Falaki just got it there. Florence Nightingale's got it. David Hilbert's got it. I really like the parentheses on that one. Those are usually, they're implied whether they're there or not, but it's sometimes fun to just put them in there, particularly for what we're doing. Cool. That is the way that we can represent the volume of this shape. What we did, to kind of summarize what we did, we figured out what's the area of the cross section. How can we describe the area of the cross section, which in this case was a circle or a filled in disk, really, because a circle doesn't have anything inside of it. It's just the boundary. The disk would be everything inside of the boundary of the circle. So minor things. Cool. So let's like formalize that a little more and we'll wrap it up. So, we basically, again, what we did is we took the area of the cross section, came up with an expression for it, and then we integrated from the bounds, like the x values that of the region that we initially rotated. So here's a different one. This is x squared from 2 to 4. We were just doing from 0 to 3 on x squared. Here's a different one for 2 to 4. Now, I also drew in a representative rectangle here to help us think about, that's a nice way to help kind of remember, like, what might the radius be? And in this case, again, we're thinking the volume of this particular shape is going to be pi times the radius squared, because the cross section, when you cut it perpendicular here, you're going to get a circle. The thing is just coming up with what's the radius. And that's what representative rectangle is really helpful for, is by drawing it in, you can help figure out what's the radius here. And the height of representative rectangle is the radius. The width of representative rectangle is the variable you put at the end, the dx. And if I rotate representative rectangle, it goes along with this and makes the same kind of shape wherever I move it. If I move it right there, right here, anywhere along this. It would still show me that. So to take that a little bit further, it would be the volume equals, again, a to b pi f of x squared dx. But specifically for this one, I could say it's the volume from 2 to 4 of pi times x squared dx. Obviously, I can simplify that like almost all of you did on that very last slide of the Desmos activity. I left it like this to emphasize the fact that there was the function squared. That was the radius squared in doing that. Now, you can totally simplify it. And if you're going to evaluate this by hand, which I'm encouraging you to try for reviewing and remembering how we do that, you probably do want to simplify that to make it easier on yourself. All right. That's it. So here's your assignment tonight. There's going to be at least 4 parts to this assignment, and at the moment, none of them is longer than 4 problems. So this first assignment is 4 problems of setting up an integral trying to find the volume of a region, and then evaluate. You have 4 of them, they're out of the book. I would encourage you to start working on them right now. You can probably get at least 2 of them done. Plus, by working on them right now, you can ask a question or 2 so that you have that reinforced immediately. On that note.